Hi everyone, so today we're going to be discussing how to hack using UART. First, it's important to understand what UART is. UART stands for Universal Asynchronous Receiver Transmitter, and each UART has a receiving pin and a transmission pin, and communicates with the other by transmitting packets into the respective pin. The term asynchronous simply means it transmits data regardless of the clock. Now I mentioned the term packet, but what is a packet in this case? So this is a packet. These packets can differ in format, but they're all a series of bits with more or less the same structure. They have a starting bit indicating that the UART is going to be transmitting data, and an ending bit or two to signify the end of the transmission. In the middle, we have data we want to transmit, and there's also the possibility of a parity bit. Now I just want to explain these parity bits a little bit so you're not confused what they are. The parity bit is basically just used to detect errors in transmission due to noise, and it can represent if the number of ones in the sequence is even or odd. So for example, if we had an odd parity and we wanted to transmit the sequence 0, 1, 0, 0, then the parity bit would be 0 because the sequence already contains an odd number of ones. And if the sequence we want to send is 1, 1, 0, 0, then the parity bit would be 1 to make the number of ones in the sequence odd. And in this way, if we send the following sequence, and receive either of the following, then we know that something went wrong in transmission. Now I'm just going to give a slight demonstration about these UARTs, and in our demonstration there is no parity bit, there's 8 bits of data, and 1 start and 1 end bit. And the sequence gets transmitted, and now if we take a closer look, we see that the sequence has a 0 as a start bit, and it has a 1 as an end bit, and the bits in the middle are data. And the data contains the least significant bit first. So if we change to big endian, then we get the following, which is the same as OX45 in hex, which is the letter uppercase E in ASCII. Now, a UART can send these signals very, very fast, so reading them will produce output in ASCII that can be easily understood. But how will this be used in real life? Well, here we have a rather dusty bottom to an Amazon Alexa, but what happens when we take off the rubber covering? Okay, so what's this? Here's a diagram of that mysterious pinholes. And here we can see UART-RX and UART-TX. And this means that we can apply our knowledge of what we just learned. So how does it work? So we have our UART, we have our Alexa, we have our computer, and now we're going to connect our UART to our Alexa, so ground to ground, RX to TX, TX to RX, and so on. And next we're going to hook it up to our computer. From our computer, we now have to identify the packet format as well as the baud rate or the frequency of the UART. Now there are many different ways to do this, but one of the easiest is to let the program do it for you. And one of these programs that can do this for you is called the bus side, and we could just use it to run the following command, and we'll get the following result. It's going to listen for a bit and reason out the exact configuration we need to communicate with the UART. Now we can watch our Alexa boot up. Unfortunately for us, after it boots up, we don't actually get put in a shell, and there's no way of interrupting this boot up. However, this message is very interesting and intriguing because the card it's talking about is an SD card. So it tries to boot from an SD card before it actually boots up the system. So what we can do is if we have our SD card and we connect it to the right spots in our pins, then we can do some devious things. So basically, now we can set up our own environment for the shell and launch it in root. So we can see in the system, there are many different parts of this Alexa, or partitions, and the main OS, or the main shell, is going to be in either main A or main B. And once we figure out which one's in it, which one it's in, then we can set up our own environment in that so that we get root access and we actually get put into the shell. And finally, bam, we're in. Now, before we move on, I think that it's important to acknowledge the pros and cons of this method of hacking in the perspective of if you're a hacker. The pros are first of all, it's difficult to detect once it's finished. So in Amazon Alexa's case, it's going to be very hard to know that the device was tampered with because once you put the rubber piece back on, it's going to be completely the same. Also, it's very hard to trace that you are the one that did it because with a lot of other methods of hacking, you have like an IP address, but this method of hacking, you are tampering with the device directly. And also, it's difficult to defend against. There have been some defenses that have been implemented that are going to be explained a little bit later, but each one has a workaround. And some of the cons are you have to have physical access to the device. Also, it requires disassembly of the device on a lot of devices. I think Alexa is a special case. Also, the devices are very varied, as you'll see later, and the process can take some time and some trial and error. Now, I will hand it over to Luis to explain more.
Now that we know how UART communication works, we need to be able to identify which devices use it. In order to know if a device uses UART communication, we need to look at the hardware to find the UART interface. Some of the devices that use UART communication might include Wi-Fi routers, security cameras, smart speakers, or even automobiles. Let's take a look at some devices that use UART interface and how we can easily identify them. As you can see, the UART interface can come in many shapes or forms. Some devices are easier to identify than others. In some cases, the UART interface might be hidden or removed completely from the device. Here we have a Tesla electronic control unit, which also does have a UART interface. However, this might look different than the others, so it might be harder to connect. Another thing to note is that not every device has the individual pins labeled to the hardware, so how do we know which pin is which? Well, we can use a multimeter to figure it out. For the ground pin, with the device turned off, we set the multimeter to continuity mode, and we look for the pin that triggers the sound on the multimeter. For the rest of the pins, we can turn on the device and set the multimeter to voltage. The voltage pin will read a constant voltage, usually around 3 volts. The RX pin will have no voltage reading as it is not transmitting anything but rather reading inputs from the user. The TX pin does have a voltage, but unlike the voltage pin, it will constantly change as this is information being transmitted over the device. Once we have gotten access to the root and are able to span a shell, what do? With the shell, we can get a device's firmware information, access encrypted memory within the device, find vulnerable functions, which we can use firmware exploits, and we can also run our code in the device to gain remote access, which is what can be done when hacking into the Amazon Echo. With access to the shell, we can turn the Amazon Echo device into a wiretap. We basically run a script that continuously writes raw microphone data into a FIFO pipe, which can be then streamed into the remote device, like your machine. We can have the data be saved onto our device and then converted into an audio file, or we can directly play the data in our speakers. This allows us to actively listen to anyone who is using the Amazon Echo we're in. Now, a big question to think about is, how was this patched? The vulnerability was found in the 2015 and 2016 editions of the Amazon Echo. Basically, these models allowed an SD card to be booted before the internal eMMC and allowed us to interrupt the boot process. This vulnerability was patched in 2017 edition. What Amazon did was that they joined the 3V input pad with the MOSI CMD pad somewhere on the board. This disables SPI communications with an external SD card and effectively disables external booting. Lastly, here are some challenges that we came across. Some companies disable their serial console before the device is shipped to the customer. The shell might be restricted for only a certain amount of commands. We can also have an only read console where no commands can be run, and we might need a secret key to access the login shell. We can still go around these issues in many ways. For example, for the restricted shell, we can try command injections to bypass the restrictions. We can still get a lot of useful information from the read-only console, like boot logs, encryption keys, and crash logs from previous times we tried to hack the device. It might be a bit harder to get across accessing the login shell, as the secret key might be randomized every time the device boots. And that's our presentation. Any questions?